on pages 93 and 94. So this is a little foldable. You cut it, and we're going to kind of write some things on top and underneath. So we need to talk about this concept of this stuff called enthalpy. Enthalpy is, it has a variable, and we don't use E because E means something else. Let me zoom in for us. We use H for enthalpy. And what enthalpy measures is the total potential energy in a system. And it's kind of difficult to just say something has a certain amount of enthalpy in a chemical reaction. So what we normally do is we talk about how enthalpy changes when we go from reactants to products. And there's all different kinds of enthalpy. We, in this class, are only going to talk about two specific measures of enthalpy. We will talk about the enthalpy of formation is the first one. And the variable that we use for enthalpy of formation is, like I said, we normally measure how things change. So we'll do that delta and enthalpy, and then we put a little tiny f down here to say this is enthalpy of formation. And so what enthalpy of formation is enthalpy associated with the formation, that makes sense, of 1 mole of substance from its elements. So it's the formation of 1 mole of substance from its elements. So, like, for example, sodium chloride was formed from the element sodium and the element chlorine. And so there's a certain amount of enthalpy that's associated with that process happening. And so an example would be something like K, potassium, which is in the solid state, reacting with chlorine, which in its elemental state is diatomic, and it produces KCl, which is a solid. And I specifically said in this definition that it's 1 mole of substance. So I have to force this coefficient to be 1. And so this is the one and only time where balancing with fractions is going to have to work, because I have to force this to be a 1. So that means this has to be a 1/2 for this to work out. So this is the formation of 1 mole of KCl from its elements, K and Cl2, and there is a certain amount of enthalpy associated with that process happening. So the enthalpy of formation for this specific process is negative 435.9. And the unit of enthalpy, it is a form of energy, but we typically report this in kilojoules. And since it was for 1 mole, we just say kilojoules per mole. So that is the enthalpy of formation of 1 mole of KCl. We do need to note that enthalpy of formation for elements, including diatomics, is 0. So if the definition of enthalpy of formation is that the amount of enthalpy associated with the formation of 1 mole of a substance, well, elements don't form, like they just naturally occur in the universe. And so there's no enthalpy associated with the formation of elements. That's just 0. And since diatomics, that's how they're naturally found in the universe, is as things like Cl2, H2, those are 0. The other type of enthalpy we talk about is what's called enthalpy of reaction. And so we still use delta H because we measure enthalpy as the change in something. And then we use that abbreviation, RXN, for reaction. And so what this is, it's the enthalpy associated with a chemical reaction that's taking place. So something going from its reactants to its products. Reaction. There we go. And there's an equation for this, and this equation is on your formula chart. The one that's on your formula chart has lots of symbols that make it look really, really complicated. And so I'm going to simplify this for us a bit. And so what you have to know is that to find enthalpy of a reaction, that's going to be equal to the enthalpy of formation from our products minus the enthalpy of formation from our reactants. And so it seems really complex, but it's really not that bad. All you have to do is you take the total enthalpy of formation of your products and you subtract the total enthalpy of formation of your reactants. These enthalpies can be found in a chart. And so I would either tell you what they are or I would give you a table that looks something like this. And so if we're like trying to work one of these out, I just find the substance on here and then the enthalpy is given to me in this chart, the enthalpy of formation. So let's do one example in the notes, and then we'll work one out on that little practice page. So the example I have for us is if I have this reaction, 2C2H2 in the gas state, reacting with 5O2, also in the gas state, producing 4CO2 in the gas state, and 2H2O, also in the gas state. And I want us to figure out what is the enthalpy of the reaction. What is delta H of this reaction? So to do this, I would have to tell you that the enthalpy of formation for C2H2 is 226.77. I would have to give you that information, and that's kilojoules. The enthalpy of formation for CO2 is negative 393.5. The enthalpy of formation of H2O as a gas, because that does make a difference. So when you're looking at one of these charts, you have to make sure that you're paying attention. Like H2O as a gas is different than H2O as a liquid on here. I can't remember where it's at. It's right there, as a liquid. So you got to make sure you pay attention to the difference there because the state of matter does affect what the enthalpy of that formation is. And so this one is negative 241.82. And then recall that we said enthalpy of formation for elements, including diatomics, is 0. So the enthalpy of O2 gas is just 0. So here's all you do. It seems complicated, but it's not. You take the coefficient and you multiply it by the enthalpy. So for this guy, I got 2 times 226.77. And then I'm going to add that because I need the total from all of the reactant side to 5 from the oxygen, but that guy's times 0 because oxygen has an enthalpy of formation of 0. And then I do the same thing over here to the product side. I got 4 times negative 393.5, and I'm going to add that to 2 times negative 241.82. So I kind of crunch those numbers and I keep the reactants separate from the products. So on the reactant side, like when I do this math right here, I find that this comes out to be 453.54. And then over here, this all comes out to be negative 2057.64. Well, now I can I'm prepared to put into this equation here, this like simple subtraction. But just remember that it's products minus reactants. So when you're reading this from left to right, it's going to be backwards. So when I do delta H of this reaction, I have to do my products number, so negative 2057.64, minus my reactants number. And be careful about the signs because sometimes this number might be negative. So make sure you pay attention to that. Here it's a positive. And when I do that little math real quick, I get negative 2511.6. And the unit of delta H is kilojoules per mole. So that's how you find the enthalpy of a reaction from the enthalpy of formation of each of its individual components. And so I talked about it, but maybe in your notes, put a note that we have to multiply by the coefficients when you're figuring this out. You have to multiply by the coefficient in these processes to get that all put together so that you don't get these numbers being too small. So you have to multiply by the coefficient in the balanced equation, multiply by the delta HF, add together all of the reactants, do the same and add together all of the product side, and then do products minus reactants to find your overall delta H of the reaction. So we need to talk about these two terms, endo and exothermic, and how that kind of connects together with that delta H. So exothermic means that energy is leaving, heat is leaving. And so oftentimes we graph this in terms of what does that look like on an energy profile. That's what we would call this. So like down here, this would be as time goes by. And here we would be graphing energy. So this is E is energy. And so if it is exothermic, that means our reactants are starting up here with high energy and our products have lower energy because it's exiting the system. And so a graph for this would look something like that. So the reactants start higher than the products. Reactants are high, products are low because it's exothermic. So you can think of this as if energy is leaving. And remember, we've talked about energy as being heat. So energy is leaving. So let's kind of summarize that under this flat. So if it's exothermic, that means heat is released. Well, how does that connect to delta H? If it is exothermic, you are going to find that delta H is negative. Anytime you have a negative delta H, that means heat is being released. And what that feels like to you, if you're watching this reaction, you are going to feel that heat. It feels hot. If you put your hands on the beaker, it's going to feel hot. An example of an equation of what this would kind of look like, calcium oxide. If I put some of that into water, it's going to make calcium hydroxide. And we could say that it releases this amount of energy. Heat is a product. It is being released. So when I'm thinking about my delta H here, since it's being released, I would say this is negative 65.2 kilojoules per mole of energy released when this happens. So endothermic is kind of the opposite of that. If this is energy over here, and this is how time is progressing, my products start higher, or they end higher than my reactants because energy is going into the system. So this graph would look something like this. The reactants start low and the products have higher energy. So if this was energy here, energy is put into this process to make it happen, to get it from the reactants to the products. Sort of like if you think about holding an ice cube in your hand, Well, that ice cube, that solid H2O, pulls energy out of your hand. So you are putting energy into the ice, and then we get the liquid water, so the products. And so under the flap, this means heat is absorbed. So energy is absorbed. Well, when we're talking about delta H, we find that that is a positive value. And just like we talked about in that ice example, how does it feel to you? It feels cold to you. And the reason it feels cold to you is because the energy is being taken from you so that the ice can go from its solid state to its liquid state. So that's a pretty good example. So going from solid state to get to liquid state requires some energy. And so we put energy over here as a reactant. So if energy is a reactant, then that means that it's going to feel cold because it needs it to be put into this reaction so that we can get something different out. And so if it's on the reactant side, delta H is positive because energy was put into this system. Okay, so let's do one example on this page, and then you guys have the rest of the time to finish this up. So we got NaOH in the solid state, HCl, NaCl, and H2O as a gas. And so all of those things can be found down here in this table. And then just remember that it's delta H of the reaction must be delta H of formation from the products minus delta H formation of the reactants. So it's always products minus reactant. It's kind of like that whole final minus initial thing. Products are what we end up with, and reactants are what we started with. So final minus initial. So we find NaOH down here as a solid. Has a negative 426.7 kilojoules per mole. And this particular equation is balanced with all ones. So negative 426.7 times 1. And we're going to add that to HCl as a gas. So I find that down here, negative 92.3. So when I do that math, which I haven't done yet, negative 426.7 plus negative 92.3, I get negative 519. So that's for the reactant side. I'm going to do the same stuff for the product side. And again, it's just a 1 and a 1, so I don't have to multiply by anything. But like here, I'm going to have to multiply that by 2 before I add it all together. So I find NaCl. So NaCl down here is a solid, negative 411.0. And then I add that to H2O, but make sure that you get the H2O as a gas, which is negative 241.8. 1.8. So then when I add those two things together, negative 441 plus negative 241.8, I get negative 682.8. That's the product side. And then I do products minus reactants. So delta H of this reaction equals negative 682.8. That's the product side, minus negative 519. And then just calculate that. So I already have my negative 682 minus negative 519, which gives me negative 163.8 kilojoules per mole. And that is how you find delta H of reaction using enthalpies of formation. So take the rest of the time to work on this. And there's not going to be a UT Quest over this particular concept. But if you have not finished your other UT Quest, now would be a great time if you need to work on that.